Welcome everyone to not 16 threads, 64 threads, no, 256, Epyc 9754, AMD Zen 4 threads here. We were given access to such a system and we will talk about performance soon. So what's better than Ryzen and Threadripper, obviously Epyc performance. And it's a little bit deja vu, so Sun loaned me 6 weeks in around 2005, the Sun T1 Niagara T1000, which also had many threads, however that were back in the day. And the problem is, the short problem is, I will make more dedicated video about this awesomeness of performance of data center business and dependable performance in the coming videos and the main channel. So don't forget to share, like, and subscribe. But to summarize this, the common problem is that we have too many cores for not very threaded code. So the spoiler is most software needs to be vastly rewritten to actually obviously make use of all those cores. And with rewritten, I mean, so we normally have code, all right. This is shell code. We will optimize some things. Illustration purposes only, and also my opinion, people recurrently tell me, yeah, but my shabby shell code, of course, not only do I fully master C, C++, and some Rust, in my opinion, for building a Linux distribution like we do here on our channel, shell code is actually fine language to script stuff, and otherwise in C and Rust you would only write orders of magnitudes more code for all this fine-grained IO, CTL, file check and what's not. And also it's actually kind of like nice readable pseudocode for you playing along at home. So like this shell or other C Rust code, if you write imperative code, it is executed one translated instruction at a time on one thread, right? So most software, like if you naturally write software, and it's also theoretically, I will probably make a more dedicated video about like programming 101, right? 5 years in the making, probably soon masterclass in actually real computer science and not this Linux distribution scripting. But the long story, the initial summary is already, whether you write shell, C++, or Rust code, if you just write code, imperative code, it is single-threaded by nature. And so dedicated video probably, if we want to make use of this embarrassingly parallel future of computing, we basically need to write software wholly different from applications and so on. And so one common thing is, if we build our Linux distribution, which, spoiler alert, the last days I built T2 on 256 Epyc 9754 threads. One common, I knew this before and I said it before, right? I said it before access to the system here, even with my shabby Ryzen 7950X, which has already 32 threads of 16 cores. And even with that, I knew since, like, I knew before many other people with a Sun T1 system in 2005, we have single-threaded code and so many, embarrassingly many threads, right? So the challenge is changing software, transitioning software to this parallel future. And in this case, so again, C applications, right? Sync your browser, like basically everything here is single-threaded, right? And in the case of building T2, I also said this already 100 times, this overly long single-threaded configure runs, right? What does it matter if 256 threads build your Firefox in 5 minutes if the configure scripts also run 5 minutes, right? Or at least 2.5 minutes. Especially in the case of this Epyc, the maximum clock is only 3 point a little gigahertz, so that is nearly only half. So basically all the configure scripts run with half the performance than my desktop Ryzen here, right? And this is systematic through all of this, right? So not only full-fledged applications need to be entirely rewritten to make use of this Epyc performance, but for software developers, super annoying, this configure and install stuff, right? So what you see here, it's like, yeah, this is configure, right? Or actually this is configure, and then embarrassingly parallel overload. I want to do one thing today, and also how to fix this, right? I mean, so one, if you do not, and by the way, all this configure stuff could be, like if this configure stuff or modern CMake and Ninja, Meson and so on, it's like, yeah, now we have 24 build systems and they all suck, right? I said this also 100 times already. A decade ago we had 3 build systems, like only Makefile or AutoConf or who knows what. And now we have 24 of build systems that all suck even more, right? And do not even solve, like they solve nothing, only differential new complexity and learning curve. And basically most of the configure tests could be completely fully parallel, right? If instead of rewriting serialized configure stuff in CMake and Meson, if someone actually would have spent some work on something useful, because like checking for headers, checking for other stuff, most of the stuff is completely independent from each other, right? So actually we could, if we would have a good configure system, which, spoiler alert, we have none. I mean, yes, GNU AutoConf sucks, but all the other solutions are neither solutions nor are they better. But yeah, we could check in parallel if there's math header and other stuff. Like we could also check in parallel package config. Like we could fork 100 times of package config, glib, GTK, whatever all those packages want to check, right? But instead we bash and even Firefox runs 4 minutes with just 3 gigahertz on one core checking for all the stuff. One thing to mitigate this, which what I already did with my Ryzen and obviously now more with this Epyc system, I just built whole ISOs, right? If you cannot, I mean, obviously I cannot rewrite 5,000 and counting open source packages to configure in parallel, except maybe another day. So what I did on the Ryzen already, which you have seen me previously, and years ago I a couple of times deadlocked it because I didn't have enough memory, right? I built whole ISOs, right? I have 33 system configurations from ARM to RISC-V to build, all built in about 2 hours. So instead of building one at a time, I just build like 6 or 8 in parallel, staggered, so that they don't overlap. Because if they are synchronized, then most of the time big packages build at the same time, meaning big packages like Clang, LLVM, the Linux kernel. And a couple of times, due to Linux kernel memory overcommit, a couple of times I fully deadlocked my Ryzen system until initially I didn't even understand what's going on until I realized, like, the compiler and stuff, 32 threads here on Ryzen, LTO and so on, actually deadlocks Linux crystals. So 2022, last year or so, you still with memory overcommit, you easily deadlock your Linux system. Amazing. So yeah, one simple, like 1.0 engineering approach, just build like 33 Linux distribution ISOs in parallel. Sure, we can do that, except the system has only 256 gigs of memory, I believe. So we might deadlock it too. So we need to be a little careful of like not over committing memory too much and stuff. Anyway, so that is the zero engineering approach, which I've done for quite a while. And the next approach is for building T2 software, here with our Linux distribution, to build whole packages in parallel, right? Currently, if we build something, let's just illustration purposes only, right? And then we get to some code. If we build just like, we don't have this arm, we have that arm. So currently in T2, scripting, in good old-fashioned scripting from 20 years ago, when we only had one processor and no other threads and no other cores, and at a maximum of dual SMP, 2-socketed 2 processors, like we just build one package at a time, right? So obviously the next big thing is, for which we already prepared a little bit, this year I majorly cleaned up our dependency handling. So of course, many packages we could build in parallel, right? So next would be change our programming here in whatever language, Shell or C, C++, you might fancy. Obviously, explicitly parallel running, like building, setlib, and like stuff. Of course, it's complex and error prone. Like this is real engineering of computer science graph theory. of actually handling dependencies. The devil is in the detail, right? It's not, it sounds easy, just some first semester university graph handling or so, because the dependencies are not like single level linear. We have better dependencies now, like GCC needs setlib and a C library and so on. But we also have stage dependencies, we have a cross compiler, so yeah, and also the dependencies, we automatically create them. The question is then, are they 100% correct? And then, like, if you do that, I mean, first you need to do all the engineering to have that somewhat work, and then you probably, from my experience, I already know, even if you have finally like spent weeks of engineering that, you probably get random build errors, because then, like, this is linear and reproducible. If you parallelize it, if you fan that out, then I'm very sure we will get highs and bugs of this build before that dependency, and then some package might miss some optional dependencies, even stuff like free type or might, and so on, right? So the devil is definitely, so that will be a monstrous project. I will illustrate that. One thing I wanted to do today, which is actually basically illustrating that a little bit, because one thing that annoys me already for quite a while, and I realized on this, because the irony is this Epyc system builds, I mean, not only does it build many packages slower than my Ryzen, because it has a maximum boost of just a little bit shy over 3 gigahertz instead of nearly 6 gigahertz single core boost, because it is embarrassingly parallel data center and single core boost of 256 threads is not important. So due to all the overly long configure time, if you just linearly build those packages like that, one at a time, this Epyc is actually building many packages slower due to the doubled configure time, right, at 3 versus 6 gigahertz. The other thing is, even embarrassingly long computational projects like LVM Clang, Firefox, and the Linux kernel do not necessarily build faster. They might build at similar performance. This is more dedicated videos coming, right? So you probably do not need an Epyc at home at 10,000 pops of money at a time. Because, I mean, obviously, like Linus Tech Tips Gaming's, like, yeah, obviously that's not for gaming. And even I knew it will be challenged to load so many threads, but I underestimated how much longer the serialized times are, right? So to illustrate that, I wanted to change one thing. As usual, summary already, yeah, you give some reasonable summary. It's basically university lectures, right? So one case in point is our MK initrd, which obviously is also serialized, because even though the main part, and that is exactly the same like configure, right? It's not only configure, it's also other serial things like initrd, right? So this Epyc server builds the Linux kernel faster, but then the initrd time is it's like 20 seconds. This is on my Ryzen, right? A little bit nicer to type here without latency, and welcome everyone. So this is just like configure, and so this is basically a good illustration of this could be just Firefox. This ignores that this is shell scripting, right? But this is one thing. And obviously you can still optimize the heck out of this, right? Shell programming doesn't need to be slow. Here are some low-hanging fruits. I have this optimized already because it annoys. Also now we messed here some shell. Let's do it up. So yeah, because it annoyed me already for quite a while that this is even slow on vintage and retro, right? So 2023 with our T2 Linux, you optimize something not only for latest AMD Epyc Bergamo, but then also for vintage and retro, because obviously on a Spark station with 40 megahertz, it's even slower. And what happens here is, so this can be optimized in two ways. One is like normal single-threaded optimizations, which I have already some. For example, we scan here all the Linux kernel modules again and again, because we like other distributions, we have here some list of like, we use regular expressions, like real professionals use regular expressions, right? Also, if you're not yet familiar and know them one-to-one by name, probably get into regular expressions. You can use them for everything. So we match some stuff like file systems, all of ATA and SCSI, like Fusion and other stuff, nice to have. Some crypto algorithms for your loops for disk encryption, some USB stuff. So basically all the most minimal things you would want in an early boot initrd, in whatever ways other distributions do. And so all those modules are processed again and again because many of these modules have dependencies, right? If you, also, thank you much. Is it mod info, was it A, like USB storage? Probably. I don't know, I wanted all. How's all? Deps. What is even the? Description, license, I wanted. Set field, print field, description license, file name, use, no, print only field, probably I use field depends. Depends. So no other, anyway, does also. So we are checking many modules again and again, right? I had this already optimized with professional shell scripting, a hash table. And this could still be a little bit more further optimized, for example. So, I mean, I optimized this already somewhat 10 years ago, but it still leaves room for improvement, right? So there's still a little bit of better matching, but this is, so it can, like many programs, this program can still be optimized further for single-threaded computing and for parallel. So what do we need for parallel computing, right? So one thing, we could, of course, do all the stuff in parallel, and this is a tricky part, right? I'm not saying it is easy to get so many threads loaded, like we do here, finally doing some compilation. Of course, all of this stuff is tricky, right? Maybe I would even argue it is easier in shell than in C, again, because in C everything is complex and you get use after free and other memory corruption and whatnot with all the C handling. And here's something, so like we could parallelize all this, like just fork all the stuff in the background. It's not that easy though, especially with these optimizations, and if we fork it to the background, we don't have our hash table optimizations anymore. But for example, one thing we compress this, right? I benchmark this, so half of the time is for the P3, and this is also, everything is coming full circle, right? Not only is our Linux distribution highly optimized for latest and greatest high performance stuff, but then also Vintage and Retro and the P3. So for the P3, I optimized, low memory optimized this, and since the P3, for 2 or 3 years, we actually compress those modules. And of course, this compression takes time, right? So one low-hanging fruit is actually to, for example, run the long-running compressions, right? I mean, obviously, with all the optimizations, optimize always, do not do micro-optimizations. Always, like optimization 101, optimize the big tasks, the big long-running potential background tasks first, and those are here the compression. I already run T0 here for hopefully all the threads. That is also used to compress the initrd here. And so let's run this in the background. And so we will, for this to better work, so basically we can do this in many places, over all our T2 code base and in your C and Rust program, right? And for that it's probably, I mean, this is a bit of a pity that with all those Unix advancements over 40 years, like shell scripting is still sure. We had the C shell and Z shell and other fun stuff, but I mean, it could really be more advanced, right? Thing better than Microsoft's PowerShell or whatever. Anyway, so to background this, it's just an end, right? So it's basically, if we want to compress, also obviously we could add here some more options of do we really want to compress it and stuff, but that is for another day. So that is so compressor there, compressors is just, and that is the beauty of shell scripting, right? Why do I use shell scripting? In my opinion, it's an order of magnitude more readable than Perl and Python, and more universal available. And we can even homebrew compile on Mac OS and maybe soon, and Haiku, right, previous video, and other old-fashioned Unix systems, right, and much easier than if we would do this in Perl, Python, Ruby, or whatnot. And yes, I wish we would have more advanced stuff. And thanks for rejoining. Why do you have this? Yeah, hey, it's cool that this highlights. So level 3 member for 9 months. Congratulations, amazing stuff. I should also read the other things. So, I mean, obviously, that is the YouTube live stream thing, right? If I give you some summary, it's like 15 minutes summary or 20-minute summary. I wanted to quickly do some stuff, 20-minute summary, but obviously leave in the comments below. It's probably necessary to give you some full picture rundown for you to learn something playing along at home. We have this compressor here once more, so we have firmware and modules, so that would be here. There are some other micro dependencies, we'll do this later, and that is not all the code. So what we would want to do is, by the way, RMCP, do we have some dear? So we did, and yeah, so that it's not that easy, right? There is more to this, and I will also do some other micro optimizations, single threaded micro optimizations. I need to check, so we run this here in probably a sub shell. I'm not sure if, so what we would need to do, we would need, like you would need to do in a real programming language like C, C++, Rust and so on. We need to wait for completion, right? So, because if we don't, we might compress it, or not might. If we don't wait for completion here at the end, that we don't have any background compression jobs, we will archive a half-finished initrd, right? And then we have some randomly last compressed files not fully written yet, right? In the middle of the compression. So that might be a little bit tricky, or actually, I mean, we could, yeah, so it will be tricky. So normally, we need some synchronization points, right? Naturally, I would do them here, like after the jobs. The only thing is, I believe that is spawning a subshell. Let me just quickly check that. Most likely, do we have here? This is this fancy, of course, everything group. I would need to check this. Having the same process group ID, shell grouping. Command grouping, ways to group commands, probably something of that sort. Yeah, placing list command between parentheses forces a shell to create a subshell. Each of the command lists executed in that subshell environment. So yeah, that's exactly what I remembered and what is logically. The problem with that is that we probably don't have job control, because this is a subshell. We probably would need to wait here. So probably we, what was it, jobs, right, jobs -p or whatever. So we would need here to wait here, because here, these are not, I mean, I would need to check the, I mean, that's a learning experience, right? More, it's like, yes, it's not C++ or Rust, but the synchronization details are somewhat similar. I just yesterday checked wait, but I forgot the details already. We have here, of course, some wait. If a pipeline is not executed, no, listen, I want, what was it? Process control. Where did I? Here. So wait for some, there is here all, so what we need is all. So usually I've written a loop for that. I think I need to read this. It's of course usually not as much fun to, oh wait, if no arguments are given, waits for all running background jobs and the last executed process substitution. If it's so, if no arguments are given, waits for all running background jobs. I mean, so theoretically, and that's the beauty of shell scripting in my opinion, not only readable pseudocode, but I mean, yeah, good luck doing that complex stuff in C, which is obviously why I usually don't write C. Let's just like maybe log this for illustration purposes only. So I expect. So how would this unfold? Yeah, so this exits when. Yeah, okay, so this will not even reach this. So let's maybe double check that this works as intended, like we interpret, because sometimes I cross-read the, okay, cool. Sometimes I cross-read, scrolls much faster. Is it working as intended? Maybe it does. It even happens to me, especially when I rush stuff here live on YouTube. I cross-read some stuff as fast, summarizing it as fast as my brain could, and then I overlook some detail. We need to check if this is actually working. It looks to scroll faster. There are still some other minor micro optimizations, but that's basically what it takes for everything, right? Like we have embarrassingly long phases where we have next to zero load, and like basically everything and in between and stuff. And theoretically, so this is of course a proof of concept. Theoretically, we would want some throttling because we don't want to shell bomb. Like if you do this on a Spark station, you might like obviously overcommit and deadlock your Spark station with 100 compression background threads. So theoretically, you would want some primitives. There's some synchronization primitives. Maybe we write a shell function for that of waiting for less than available threads, background jobs, just to be on the safe side. Janice is wondering why Git wasn't included in the minimal package set. Because you can just build it from source. So I also stripped down the minimal package set. I scripted further down because Python, cross-compiling Perl Python, and their packages gave too many issues. And it's actually a better user experience if we do not ship half-working Perl and Python, because we had in our magazine, which probably we should soon need to upgrade to a full wiki, we had here Frisch Install 101, and it's like basically rebuild this Perl and stuff, because this cross-compiled stuff is only partially functional. And it's similar how many Ubuntu and Red Hat probably don't ship Subversion anymore, right? If you have a decent enough system, you can just emerge it from. Actually, this is a fresh installed system, so you can just emerge it in 6 seconds or so. So like why? Basically, we are obviously constantly refining our package selection. Where's this latest version? Because sometimes we miss the latest version for data AI. Data run through today already. So like here, as it appears to be latest version, amazing. So like, okay, 13, this estimate, this is again, this is the estimate between fully, and this is only 32 threads on my Ryzen 7950X, right? On the, I can, it doesn't matter. So like, yeah, I rather ship by default what the end user experience, like Git only developer need, right? So I rather optimize the Joe user experience, which many of which install T2 on a PS3, on an SG Octane, or even the latest and greatest Ryzen desktop. Sure, a enthusiast developer might need Git sooner, but hey, emerge it in 13 or 60 seconds. It's not the end of the world. I rather optimize an UI. I would rather like shipping Firefox, right? Everyone needs Firefox. I rather, for example, the Gutenprint print drivers do not cross-compile for stupid tooling reasons. I'd rather fix the Gutenprint printer driver to be available by default. It's probably what more Joe users need for printing their e-government stuff at home at this time. Anyway, like, so yeah, we basically, yeah, best shipping what most people need. And also, I mean, obviously we also build Firefox because most people have something lesser than an 750X. So, I mean, between you need in browser instantly and it takes 15 minutes or 15 hours to build, or 15 days on, or 15 years on a Spark Station 2. Like, yeah, shipping what we can reasonably ship by default, what everyone needs, and all the small, I mean, obviously when I install T2, I also need to emerge some things, right? I would, like you would need, even on macOS there is stuff missing, right? And you need to emerge. Playing with P3, XFCE, see if it will run using this to see for compilation. I wish you luck. Wasn't for us updating patches, wouldn't be able to do this at this point. So happy that you can play along at home. That's amazing. What else do we have there? Great. And also the MIME package manager doesn't work as expected. I want to get a probably screwed install, but never install anything, no output. Well, the mine stuff works for me, not sure what you did, but I want to get rid of mine, right? Mine is an old-fashioned thing from the days of Rock Linux. Ideally, we should get rid of it kind of as soon as possible. When mine was introduced, we even at Rock Linux had a proprietary GAM-based binary package format that I transitioned then back to full source tarballs. Theoretically, the support for this GAM package is still there, which makes no sense in my opinion. But so long story short, we don't really need mine anymore. It's just a glorified tar extractor at this point, and we will fully get rid of it sooner than later. But everything takes time, right? I already work day and night. I can't do it even faster, basically. But yeah, but any comments, patches, notes, appreciated. So how far? So it looks, it appears to be much faster. And yeah, it is. So I guess we are down. So with this running this in the background, of course, doubles here the speed, right? I believe previously it's probably run like twice as long. And this is, I mean, obviously we're still with this probably not loading 256 threads, but probably getting there. And do we have, I could show you that probably. So let's just, we could do this for, so yeah, jobs. Okay, this did, already there. Let's see. I mean, this might, does this print? So there's still some micro optimizations, but certainly that is, of course, a huge improvement in performance. Should we have? Let me log into the Epyc system and show you that in action. So so that's Epyc. Some stuff. I'm not sure what's going on there. That's not my system, and it's at the other end of the world. And I currently ask if I should give them credit where credit is due. I don't want to, without checking if they want that I disclose who provides the system. If they say sure, shout out welcome, I will do. Just I want to be a little bit sensible in case they don't want their name on our channel for reasons. You never know. So yeah, Epyc, 128 core, 256 threads. And so actually we probably MK initrd, so just illustration purposes only. All right, this is booted, this is not so, this is booted, like obviously I'm building T2 on some Ubuntu, they pre-installed Ubuntu for us. This is why this is not matching. Obviously the performance would probably be a little bit higher if it would run natively T2. But that's another thing. So that is, and there you see the difference, right? This is the load. That's what we're talking, right? This is what we're optimizing. This is when you run, and that's basically the same experience that I had 2005 when Sun loaned me 6 weeks Sun T1. It's basically, it's like, yeah, this is it's basically half the performance. Like if you don't run embarrassingly parallel optimized code, it will run worse than on your system playing along at home, right? I mean, and that is, by the way, how it looks on Winston retro hardware, right? This is because it's only 3 gigahertz, as you see here from LS CPU. There might be something strange with the storage system. This system is storage bottlenecked. It's just some test systems for us to play, which I'm very grateful and thankful for. So this has only one M.2 SSD, and I'm not sure. Maybe it's getting a little bit warm. Maybe because I'm not sure. I mean, maybe just Ubuntu sucks, or who knows what. Or maybe this LS CPU maybe it just does so much stuff. Maybe it does. Does it just does? I mean, maybe just reading. I mean, maybe that's just the performance of reading 10,000 IOCTLs of 10,000 times opening files potentially. Maybe it appears LS CPU could also be optimized because maybe just LS CPU is slow on gathering 256 threads of data potentially, maybe apparently. Anyway, so let's replicate that here. Has been. I don't want to commit this yet because I have some other things to improve. Okay. And mind, this secure shell packages go half around the world, so some European shitty internet in between. Sorry for that. Shall I subscribe and curse at Vodafone for this failing latency experience? Compressor. Here, let's just background it there. Of course, normally I would commit this, but I'm not yet finished with that. I want to do some more things later. This is just for you to learn. So that probably we did wait here, right? So that is after all this stuff, wait. That probably should be enough. And I mean, probably we should have done before and after though. But let's see, how much faster is it? Yeah, that is difference of, this is already difference of day and night, right? And this is, I knew our MK initrd could be faster. It's like, once upon a time it was fast, then we optimized it for the PS3. I mean, it's still, even with this background, I mean, we probably should, for dramatic benchmarking experience, we probably should include, I mean, but this is so simple, right? And this is why I love shell scripting. I mean, it's probably an order of magnitude faster because before it was dog slow. And I mean, it's not even freaking, it's so many freaking threads. These are so many epic thread ripping threads. It's freaking not even registering on the system load, right? It's absolutely crazy. So yeah, 16 seconds. The crazy thing is this is still slower because of the lower max clock, right? This has a max clock of 3.1 gigahertz or so. So my local Epyc thread-ripping Ryzen is still doing this kind of already slightly optimized, and we run set standard compress with T0, which should, not sure, maybe it does mostly decompression parallel, but anyway, could potentially maybe do something in parallel, but maybe it doesn't do the most. Where's our clock though? Yeah, 3.1. So we have 3.1 versus 5.9-ish, my undervolted 200 megahertz PBO overwritten clock stuff. So nearly half of the performance and nearly half of the single thread performance, right? And it obviously shows here with the time. Let's quickly comment this out for dramatic reenacting performance here. Let's grab for that. Why is this not? There. Compress. Okay, that is grabbing worse than I thought. Of course, we need some better primitives because that is only the beginning, right? And then, of course, the big thing, as I said. So yeah, it's probably an order of magnitude. Yeah. So that's only the beginning. This is just one YouTube live illustration purpose only. But this is how we not only like one Epyc, one P3, one vintage and retro, SG Octane at a time, continuously making our Linux distribution one of the best, one new system log in to play with at a time. And then he asked, we got Epyc, I got remote access, right? I'm not as rich yet. This is not my Epyc. This was generously provided by other big tech players, which I will, as soon as I have permission to tell you who gave me this amazing access, I will. I just don't want to put their names on here if they don't want that. So yeah, I have remote access to play with this amazing system, which is amazing. And this is of course your share, like, subscribe, right? The more you share, like, subscribe, the more other people and companies will help us, because obviously when I go to AMD or Lenovo or whatnot, or Intel, and we have hundreds of subscribers, they react differently than when I see this already, right? When I started YouTube channel, like, as long as I was a small German Linux developer with a small little company, companies never responded, right? You write to Intel, you hear nothing. You write to AMD, you hear nothing. And even when I just had 1,000 subscribers, you write to Lenovo or Samsung, just look on my 5-year-old videos, say, you're a YouTuber, here is a Samsung Galaxy to test, here is a Lenovo ThinkPad to test, right? It's absolutely crazy. If you're a kernel developer, you're nobody. If you're a YouTuber, you're a creator. So yeah, 53 seconds. And so we improved that. What was it? 16? Oh, we don't have Lua installed. We can also use PC. Was it scale equals whatever, and then 53 seconds, or how do we do that? I think it was at 16 of 53. Yeah, some 70% improvement, so order of magnitude. And so that of course changes this kind of things. I mean, someone needs to debug it, someone needs to think about it, someone needs to implement and test it. And basically we need such primitives all over, even in our T2 code base. And of course the big elephant in the room is then, as I mentioned in the beginning in the summary, of course, building whole packages in parallel, but that is a way larger project. Today I mostly want to do the normal, regular things here. So, so that was 50, I mean, it's actually nearly 54 to be fair. And last but not least, we could quickly, what else do we have here? We could quickly build the Linux kernel. Also 10 years ago, used a small Linux distribution for an OS recovery. I had no idea Puppy Linux came from T2, at least. That's what yeah, some people, I mean, we had, you will be surprised, I guess in the meantime we did so many embedded projects, right? Probably some parcels were delivered to you. We had 15 years ago, we had even some small embedded thing with UPS. I mean, I'm doing this for 20 years, right? You will, there were some security appliances that used T2, Puppy Linux, they mix and match, sometimes they build entirely on T2. Sometimes the Puppy Linux people are a little bit funny. They change their stuff every. By the way, let's build in. By the way, so every Puppy Linux, like every year they mix and match other stuff. Like one year they build it with T2. The next year they used Slackware packages. Another year they feel like using Debian and building some stuff with. They do their thing. I wouldn't do it like this. They redneck engineer this stuff a little bit more than I would do, but that's fine. I do ours and they do theirs. They once dropped some patches. I believe there are probably some 200 changes of Puppy Linux. Like for years they sent nothing, and then Gary Bauer, whatever, something of Puppy Linux creative him. Like once he dropped me some 200 whatever changes of their Puppy Linux based code quality. I had to massively clean it up and stuff, but yeah, there are some 200-ish changes and contributed packages in in T2 from their Puppy Linux stuff. So yeah, as you see here, you don't see much load because that is the extraction, right? So less var adm log hello, or is it even also we need change root source. I think there I have it. Var adm logs of Linux stuff. So yeah, there is that building, and it's like, yeah, that is an Epyc. I mean, this are not even the problem is my terminal font is not like this. These are all the threads, right? Previously. And so this cut, so this modification should be enough to get Epyc. Of course, there's still some tarball extraction, so there obviously is still a lot of bottleneck single-threaded compilation, right? Tarball extraction, even the Linux kconfig stuff, and so on. Then this embarrassingly, but this is typical to all open source packages, right? The Linux kernel is one of the more efficient packages. Most packages like Firefox, but even Bash or all the other GNU configure stuff, right? They usually have a way, like even binutils, right? And then stuff like binutils or GCC, they even run configure stuff like 7 or 17 times, further wasting CPU cycles and loads. So yeah, this is like, if you ever wanted to know that, like this is how Epyc. But of course, unlike, yeah, this was the main build. This is already done, so probably now we mk but there you see, right? That is, and the Linux kernel is one of the more efficient packages, right? Sure, if you are, of course, building all open source packages is a little bit different of a load case. If you are only one lone single developer at home, like Linus Torvalds, and he is doing nothing but building his Linux kernel. Why is this still linking or what? So so this linked even so freaking long. Is this Clang, or do we have which even is it? Is it Clang or user bin cases? Do we not have a cases? Or did I know we should still? Do we not? What do we even build this with? Okay, this was which? Ah, this is Clang. Okay, if this is Clang, I thought we have GCC. So as this is Clang, so actually then, but yeah, but again, this is super typical, right? Like here's probably, this was probably mostly linking and stuff. So like single thread configure, embarrassingly parallel compilation until probably LTO linking, even in this case LTO linking, then other embarrassingly parallel mod probing stuff. Oops, also I clicked this now wrong. We're still building. So okay, this is, so this might be our T2 checksum creation stuff. So even our T2, okay, it is not yet that much faster, unfortunately. I mean, how much did we, I mean, we cut down from 50 to 16, right? So that is 30 seconds. So yeah, we're already 30 seconds faster of, I mean, that's obviously some improvement. So this is not, I mean, it's nearly half, but it's nearly half of my Ryzen build time, right? And that is also, previously I was sometimes like, over the last years, do I build a Threadripper? I'm also, like if AMD would not always delay the Threadripper so much, like a year, like they did now, I might have already had a Threadripper. But basically the time Threadripper is refreshed, like previously Threadripper whatever 5000 and now Threadripper 7000, by the time it's already 1 year old Zen technology, right? And then for even my Ryzen, like while we speak, I didn't even load my Ryzen, right? And for normal development, usually if I program, it's probably 90% of the time, 99% idle, just waiting for my keystroke, right? Because if a programmer programs, then big overkill workstation is idle. And that's basically the main reason why I don't have shed out over 5,000 euro for a Threadripper system even. Although Threadripper would fit more to my use case because of the higher boosting single thread performance. So yeah, so this is nearly, my Ryzen builds this in less than 8 minutes. So it's nearly twice as fast. But again, we still had embarrassingly long LTO times. And it's the same for Firefox, right? Firefox serialized, like basically all packages, and even Firefox serialized configure time, embarrassingly parallel, main build, then again, mostly single-threaded LTO linking. Like if you want performance, and most performance, whole program LTO link time optimization at the end, and then installation stuff. So it looks like probably we should also somehow multi-thread our, and all of this stuff even helps, it not only helps my Ryzen here at home, it even helps maybe the P3, which is SMT dual multi-threaded, but even my SG Octane, which I have an SMP Octane with dual 250 megahertz, right? So even on the SG Octane, like everything we now need to further modernize and parallelize will help all the other even vintage systems, or think even the previous video, right? Fastest T2, the fastest and nearly only Linux for Hewlett-Packard Precision, HPPA, high precision architecture, like dual processor UltraSpark, quad core HPPA, and so on. So it's just, previously it was not as pressing, but when you now have this modern world, not only 16 cores in your workstation and 128 cores in your server, it's like, yeah, then now there really is, like if you really want to be faster on the systems, you really need to embarrassingly parallelize your program code to take advantage. Moat asks, will using mold help out in this gen? Does it generate errors? Mold will not help, because mold, in this case, mold will not help. I mean, I also personally find mold relatively pointless, and I'm not surprised that nobody wants to sponsor that, because if you want highest performance, you LTO link that, right? And LTO, link time optimization, it's not a classic linker. It is mostly done in your compiler, right? So if you would classically non-LTO link, mold could help, but if you want the most performance anyway, then it doesn't help, because you don't have normal object files, you have pre-compiled bytecode or intermediate representation bytecode that at the end all the time is spent in your compiler for the whole program LTO linking anyway. So in that case, mold helps next to nothing. Not even sure if it would help something at all, because again, your compiler is the linker and the compiler is doing all the whole program optimization. So optimizing the compiler would help, or I mean, if you wanted a faster build, you could build with less optimizations, but yeah. More questions. Correct, said truth. Called tech reviews, YouTubers. Really? No, it's not that. Like any tech item. How long does it take to compile a generate Linux kernel? All config with Epyc. So this is kinder. So that it's so it's probably that, right? So this is our T2 default kernel. So that's basically, and this is probably with GCC. Actually, we could check that. Let's quickly. So that is config. We could build with GCC. Let's see how much faster it is. GCC here, and then ln GCC to user bin cases. Force. Both. Let's do this again. That probably should be twice as fast nearly, because Clang is slower and LTO is twice as slow, so yeah, that probably, so the build time estimate is not accurate anymore, or actually, yeah, anyway, so I would guesstimate maybe 2 minutes, potentially, maybe, time will show. Anything else? How long does it take? So this is a nearly all modular config stuff, right? So you ask compile kernel all config. So I never use all config. But this is the T2 kernel, because obviously I want, if you download and install T2 for playing along at home on your operating system media, of course I want that if you use our Linux that it just works. So of course we enable as many modules as possible. I prefer modules because I don't want to have all the unused stuff linked into the kernel image, unlike Intel's Clear Linux, for example. And so that probably should be close to what you're asking, I guess, although the details might vary and so on. So yeah, this is GCC now. I changed this, right? So, and with GCC, I'm not sure if the Linux kernel does support LTO with GCC. I guess it's not. Actually, we could check what. All right, maybe it would actually. I guess it would. But I probably would need to change some GCC. There were some GCC beneath plugin marginalities last time I checked. Maybe probably should invest. You know what? Like nothing like putting that on my to-do. Fix Linux GCC LTO. I believe that could potentially work, but currently doesn't. Yeah, so this link pause was way shorter, right? We had to, so this is configure, like tar extracting configure, embarrassingly parallel build, final linking. In this case, mold might help a tiny little bit, but it's just some seconds anyway, so who cares? Oops. And we're probably nearly done. It's our initrd, which now should be more probably. Yeah, so there are still some more. Also, this looks ugly. Not only optimization, but I should also optimize this stuff out of there. So yeah, then we had init like installation, linking, mod probe, installation, initrd, checksumming. So probably next I also need to optimize the checksumming. Probably we are done. Yeah, 3 minutes. Okay, so that's 1 minute. So that's 25. Like this GCC case is 25% faster than my Ryzen GCC kernel. My Ryzen. So this exact config with GCC, my Ryzen builds in 4 minutes. So this is quite precisely. I mean, it's. But here again, this is a consequence of not embarrassingly parallel optimized code, and probably why you don't need to save for an Epyc server at home unless you have very concrete embarrassingly parallel business database and storage use cases. But I will of course use the opportunity and continued dedication to further optimize our Linux distribution wherever we notice potential. I hope you enjoyed this, learned something. As always, it would mean a thing if you could share, like, and subscribe. I hope you enjoyed this, learned something. Have a good day or night, and I hope to see you soon for all the next fun and embarrassingly epic parallel stuff to come. There's one more question. Is Clang 17 faster when it comes? That's a good question. This is probably 16, right? Oh no, this is 17. All right, that's my Ryzen. That is 16. I believe it only became slower. Usually, I think LVM Clang only became another 10 seconds slower. Like, I believe 16 built on Linux kernel in 6 minutes 40-ish. Maybe it's now 6 minutes 50-ish. So, yeah, between LVM Clang 16 and 17. See you next time.